right, thank you for the introduction. My name is Xiang Chen. I'm an assistant professor from UCLA. I'm very excited to talk about this research called Minuet, multimodal interaction with the Internet of Things. This work was collaborated between several institutes, CMU, UCLA HCI Research, Google, and Apple. So I want to start by telling you a story about our beloved user Richard. So one day Richard arrives home and it was dark, so he picked up several Amazon boxes in front of his house. And because it's dark, he wants to turn on the lights so he can go through the hallway. So he says, turn on the lights. And Minuet interprets his command and detects his location, and he turns on the lights next to Richard so he can safely walk into his house, only to find that the cat has knocked down one of the houseplants. So he has to command the Roomba, pointing at the Roomba at the corner of the living room and said, clean this spot. So the Roomba follows the command and arrives at the crime scene and clean the knockover plant. So Richard was tired and he wants to enjoy and relax a little bit. So he points at the music player next to the TV and says, play the music, which plays his favorite playlist of songs. So as he enjoys this music, suddenly his phone rings, and he's his boss. So he's very nervous. He picks up the phone, in the meantime trying to wave down, and the music player turns the volume down. So it turns out it's no big deal. The boss simply tries to reschedule the next day's early morning meeting. So I just show you a scenario of how our user Richard interacts with Minuet via a combination of voice command and gestures with Internet of Things. So before I tell you what's happening under the hood, we need to take a step back and look at this vision of Internet of Things, or IoT. Internet of Things is becoming increasingly ubiquitous in your everyday living environment. So these IoT devices, they are usually spatially distributed in our home and workplaces, which means that there needs to be some centralized ways to interact with them, often manifested as different apps in our mobile phones. However, there is a problem of scalability. This chart shows that in 2022, we'll have almost double the number of IoT devices compared to 2016. Which means increasingly there will be more and more cumbersome for users to install, configure, and retrieve an increasing number of apps that control this vast number of IoT devices. So how can we do better? Well, we all know that voice assistants are becoming increasingly popular. Well, they kind of solve part of this problem, allowing the users to just talk to one device, which interfaces many other IoT devices. However, there's still a problem. Let's say I want to turn off these two lights. How can I tell my Alexa to do that? Left and right light. So maybe some of you might thought I should have named these two lights, maybe, I don't know, Tom and Jerry, and then I can just tell the names, and which is pretty much state of the art. You really need to have specific names or groups associated with your IoT devices. If not, you want to use voice to specify the spatial information, such as turn off the lights to the right and above the couch. You can see it's very cumbersome and unnatural. The problem is voice itself lacks spatial expressiveness. So that's one of the problems we're facing right now, a lack of expressive means for us to interact with IoT devices that are usually spatially distributed in our environment. Then the immediate solution you can think of is, well, why don't we just point at those lights? That seems to be a nice solution, and indeed, it has been explored in several previous papers using gestures in lieu of explicit app-based control of voice. However, there is still this problem of ambiguity. Look at this figure 1 of the scenario paper. You can see sometimes IoT devices can be so densely distributed that pointing might not be able to nicely tease out which one exactly the user is pointing at when they are very close to each other. So what can we do now? We can turn to multimodal interaction, which kind of combines the best parts of both worlds, voice and gesture. It's quite promising, especially if you look at earlier systems a while back, put that their system or QuickSet, both of which nicely combine these modalities, however, mostly in virtual environments. It's still yet underexplored to enable this kind of multimodal interaction with IoT devices in the real world. So that's our goal. We want to explore a design space of multimodal interaction that enable expressive control of spatially distributed IoT devices. So before I introduce you to this design space, I would like to take a look at our prototyping platform. In order to enable exploring such interaction techniques, we chose to build this sensing platform using ultra-wideband sensors. It's traditionally used to localize people or items in large spaces like warehouses or department stores. We repurpose this kind of platform using several UWB anchors. 3 or 4 anchors are sufficient to localize the user in the environment, where the user would wear a UWB tag, as in our case, as a wrist-worn device. The idea is that if we know where the user is at, and we can add an additional sensor, for example, IMU, to detect which way a user is pointing, and then we can infer what the user is pointing at by pre-registering IoT devices in the environment. So this video will show you how, our system works. And from visualization, you can see you can track the user's location as well as the arrow. And because we pre-register the 3 lamps as blue dots, we can infer which one the user is pointing at. And then in combination with a microphone, we can combine pointing and voice command, which together allows us to enable and explore this large design space of interaction techniques. So I'm going to walk through each of these design subspace one by one. But first, we can, looking at the 2 dimensions, you can see that we're considering at least 2 steps. First, selecting a IoT device, and next, specifying the interaction with that IoT device. By juxtaposing the 2 modalities, voice and gesture, along these 2 steps, that enables us to create a large design space. So the first area of interaction techniques is pretty much similar to the existing approaches of voice assistants, where voice selects IoT device and then voice proceeds to interact with it. The difference our system can make is that we can add contextual awareness. So as an example I showed you earlier, Richard is able to use his location implicitly redirect the system to turn the lights only next to him or near him. So for example, in this figure, the lights will only be turned on in the kitchen, but not in the family room next to the kitchen, for example. I'm going to show you another example.
Contextual information.
Turn off the lights here.
So very simple idea, just adding location awareness to augment voice commands. And then using gesture as a means to interact with IoT can further enable us to, for example, to specify a continuous value.
Adjust the appliances, satisfy continuous gesture plus voice commands.
So as opposed to a discrete volume up or down, the user can continuously specify the value of the volume. And then if we combine voice and gesture together at the interaction step, we can afford even richer ways of telling how IoT devices should help us accomplish tasks, such as the Roomba cleaning a specific spot. Okay, so we arrive at the second row of our design space. So what can we do with gesture selects and voice interacts? Because in our system, every user is wearing a separate wristband with the UW tag and IMU and microphone. We can use these characteristics to achieve some sort of user identification. So here example, where the presenter would point to a projector, which then displays one of his slide decks. And then as an audience member raises his hand to ask a question, the presenter can point to that specific audience member. And the two devices can establish some sort of handshake agreement, allowing the audience member to have temporary access to navigate to the specific slide where he wants to ask a question. For gesture select and gesture interacts, previously we mentioned that there is this ambiguity problem. So by adding additional disambiguation gestures, we can try to mitigate this kind of ambiguity. So here example of the user leaving the lab, but only wants to turn off his light, not his lab mates who are still working on his project. So in this ambiguation gesture can further swipe left or right to specify which one of the ambiguous lights the user wants to turn off. And as you can see in this video, another way to disambiguation is just to add an additional voice command. For example, turning off the left one. So finally, when we again combine voice and gesture and the interaction step, we can further specify, for example, as user waving down his hand, whether he wants to lower the volume or the brightness of the TV. So this allows users to have final control of exactly how they want to interact and control an IoT device. We perform a technical evaluation to see how well our system can track and sense a user's location and gesture. We constructed a simulated environment trying to make a living room out of our lab space. 10 participants interacted with 5 appliances on this 4x5 meter grid. We measured localization accuracy of 0.33 meters, and only one false positive in a total of 45 minutes of non-interaction periods. And something that we found is quite interesting is the pointing accuracy is not so much determined by the sensors, but is rather a human limitation. So imagine on average a user's pointing is off 9 degrees off the target by 9 degrees, which means that we can use this value as a heuristic to guide our ambiguous set selection. So the idea is we use 9 degrees as a threshold to first narrow down a set of ambiguous IoT devices the user might be selecting. And then we further ask user to, within this small set of devices, to disambiguate and pinpoint exactly which one they want to interact with. We also gather some qualitative feedback. First of all, it's not surprising to see that users found pointing at a device to interact with is natural and intuitive. Most users commented that Minuet complements existing voice assistants, allowing them to perform easy object classification without having to name or group each single IoT device. Something that's a little bit surprising was that the first order of consideration by the participant is not so much the expressiveness we thought about, but rather the appropriateness of modalities. Participants thought that Minuet provides them with more interactional options when it comes to interacting with IoT. For example, one commented that compared with Alexa, I don't have to talk if I don't want to, but still being able to control the device. So by having Minuet as a complementary system, the user can choose which modality they think is the most appropriate at a specific context. To summarize, I presented Minuet, a multimodal interactive systems for Internet of Things. By leveraging the UWE localizing and system together with IMU sensors and a microphone, we can enable a large design space of interaction techniques, allowing users to use a combination of voice and gesture to interact with IoT devices, spatially distributed in our environment. With that, I want to conclude my talk. I'm happy to take any questions.
Thank you. I had a question about pointing, absolute pointing. What do you use for the yaw or angular sensing for yaw? What absolute would you use?
We use an IMU sensor.
So is it a compass?
An IMU sensor has a combination of accelerometer, gyroscope, and compass.
Yeah, because you need the absolute to know where you are in the room. So the compass gives you the absolute.
Right.
Thank you. I really love it. My question is coming from the world of paranoid consumers, because your microphone's not on all the time.
Mm-hmm. That's correct.
How do you resolve that?
So in our system, the microphone is only on when we detect the onset of a pointing gesture. And usually, to be honest, it's not exactly at the onset. It's 1 or 2 seconds. There is a 1 or 2 seconds buffer. So we only process the user's command 1 or 2 seconds before the onset of a gesture. So this would allow the user maybe to say the command a little bit earlier prior to pointing, because we don't expect the user to point and then exactly at the same time or after that to say the command.
But it's just like stretching your head, is it activated?
No, our gesture onset detection is very robust. Only one false positive over 45 periods of non-interactive activity.
Just index finger?
No, it's an onset is this motion of pointing at a specific object in the environment.
Any other questions?
So there are at least like 3 things that are like influence the accuracy of pointing, right? One is the IMU drift, and then there can be multiple objects like on the same line of sight, and then there's the wrong dimension that is the user perception where it's from, right? So for this last one, have you tried adjusting the pointing? Because sometimes people, instead of using the vector, they would actually use the eyesight to define where they're pointing. Have you experimented with different ways of computing?
I think one effective way is to show immediate feedback. We thought about maybe adding an LED module to one of each IoT devices, or adding a laser pointer at the user's wristband, which can provide a feedback loop guiding the user how to adjust the pointing. But there is this concern of, in the first solution, there is an instrumentation cost. And in the second solution, there is this maybe privacy appropriateness. You don't want to shoot a laser pointer all the time whenever you want to interact with something. So this is something we are still exploring in our future work.
All right, let's thank the speaker again.
All right, thank you.